Okay, in this lecture, we're going to try to do some mathematical modeling or numerical modeling using Python and the basic Python we've learned in the previous lectures. And we're going to focus on the biggest thing right now, which is the epidemics. And we'll see how we use a set of mathematical equations to describe something like epidemic and use Python to solve those equations. So in the last lecture, which is also a special lecture, we learned putting everything together by using program controls, NumPy arrays, and pandas to visualize the data. And also we learned regression, which is curve fitting, based on curve fitting to predict what's going on. And sometimes it works well, sometimes it doesn't. So in this lecture, we will apply Python knowledge to model the evolution of epidemics using mathematical equations, and we're going to go through mathematical descriptions for infectious disease. And we will show how to solve those equations using Python, which is quite straightforward, and how to visualize, analyze, and interpret the results. So the COVID-19 outbreak, which is currently now, it's everywhere. And you've seen it's growing and changing. And we've learned using pandas and NumPy arrays and matplotlib to generate plots like this, which is a line plot showing you the variation of the cases and other things. And this is the previous lecture. In the next lecture, we will learn how to generate a map like this, filled with the colors of the cases and other parameters. But today, we're going to look at some of the basic science behind epidemics like this, so which is called modeling. So why do we need modeling? Because modeling helps interpret the data, at least to some extent, although data is the key. And best way is always to get the data, but modeling helps the data. Right, so if you still remember this plot, and we generated it using pandas and matplotlib and NumPy, and you will see that these are the temporal variation of the number of cases with countries greater than 10,000. Right, so when you see this, and you will see a couple of things, like you can see that different countries started to have this growth in the numbers at different time, and in places like this, like in China, it's already ended. Right? You can see that this line curved around mid-February, and now it's saturated right now. And you can see that it takes about 40, 50 days to get from the exponential growth state to linear growth and then to saturate. And then you will see others, and the question is like why it's saturated. And then you will see others like like this curve, it's growing almost like exponentially or linearly. And then people will ask question when it's going to start to saturate, and how long does it going to last for this kind of growth, right? So modeling the process of things like this are actually extremely complicated, and there's so many other factors to consider, but there are some basics behind this, and you can see even from simplest math, and you can still learn some basics about the dynamic evolution of epidemics like this. Right, so let's gonna start with the exponential model. So if you still remember the exponential model, so we have in the exponential model, and we will say the first assumption that starting from day 0, and we have number of infected, which is called I0, or I square bracket 0, that's day 0. Right? So the assumption is that every day, each patient will infect some amount of new patients, and that ratio is fixed. It's called R0. So the delta, so at day 0, so how many new patients are created? So that's R0 times the existing patients, right? So you add this term to R0, and that's the day day one of the number of patients infected in day 1. So day 1 equals to day 0 plus R0 times day 0, right? So the same idea at day 2, and you do the same reproduction, which is R0 times I1, and then you got day 2. So R0 here is a constant, and which also the growth of the model, right? So if you look at this, and you can kind of get this recursive relation, which means that n plus 1, so n is day, starting from 0, 1, 2. So the next day equals the previous day, which is existing infections, plus the new infections in this way, right? So you can see this is the infection on day n plus 1 equals to the existing infection on day n plus the newly created infections, which is R0 times IN, right? Because each, that's assumption number 2. So each patient can create R0 new patients, right? So the total new patients is R0 times IN. So that's called recursive relation, and we can use Python to calculate this easily using a single for loop. And let's see how we do. So before we do it, I want to show a couple of mathematical notations down here. So the mathematical form of the exponential model goes like this. So IT is called infected. So I is a function of T is time, right? So the function, the mathematical form of the exponential model goes like IT dot here. So that's actually called the time rate of change in I equals to R0 times IT. So which means that increase is proportional to the number of patients within one day. So within one day, and then the new patients will be I times R0. So this RT and with a dot here is called the time rate of change in IT. So if you look at the definition, time rate, so that's the number of cases divided by time. So let's take a look at what does that look like. So the time rate of change on day n plus 1, so that will be the changes in the cases. So that's I n plus 1 minus IN divided by change of days. So that's 1 day. So that's I n plus 1 minus IN divided by 1 day. So that's 1. So the time rate of change at day n equals to IN plus 1 minus IN. So that's a very straightforward relation. So if you plug in this relation to that equation, and you get the recursive relation right here is IN plus 1 minus IN equals to R0 times IN, right? So that's exactly the relation we use for the exponential model. So how we use a Python code to make this model working. So this is the basic simple code that we use. So we will use the NumPy array, import NumPy as NP, and we also import matplotlib.pyplot as PLT. So we have, say, t equals to 11, that's an integer, that's the total time of simulation, say simulation days. And R0 is the base infection rate. So every patient creates 2 new patients. That's actually a lot, right? So now we defined an array as I equals to np.0t. So that's an array with the same size of the simulation day. And then we also initialize the data. This is called initialization. We initialize the patient on day 0. There's 1 patient. So I0 equals to 1. Right? So based on this information with T, R0, and I0, now we can use the recursive relation to calculate the day 2, day 3, day 4, all the way to day T minus 1. Right? So this is basically the code. It's a for loop that solves this equation. And you can see that, let's take a look at this for loop. So we're doing for n in range T minus 1. So remember that t equals to 11. So that will be range 10, right? Which means it's from 0 to 9, right? Because 10 is excluded. And why it's 9, why it's t minus 1? Because the recursive relation goes from, it's not n, it's actually n plus 1, right? So when n equals t minus 1, and this equals to t, right? So that's going to be, well, it's actually t minus 2, and this will be equals to t minus 1. So that's actually, otherwise, if this is not t minus 1, you will see it's an index error, and you're trying to access the index that's longer than the array itself. Right? So the key here is to do the recursive relation. That's exactly what this equation is, right? So the next day, n plus 1 equals to the previous day. plus R0, which is the new patient, times I in this way, right? So n is starting from 0, 1, 2, all the way to t minus 2, right? So this is the plotting routine, and we will see plot I as a function of time because it's from 0, so it actually doesn't matter. Let's just do this. So you can see that if I use R0 equals 0.2, and initial infected people will be 500, and after 30 days, I got about 175K patients in this way. And then if you look at this data, look at the curve from the US in the first month starting from March 1st. That's a figure we got from yesterday. And you can see that the exponential curve, looks more or less like the data. But as time goes on, that's not necessarily true, right? So the exponential curve works pretty well for the first couple of few days when days are days number small. So the problem here, and let's take a look at it. So if we keep running the model with T11 and R0 equals 2, so after 10 days, and you can see that I have 60K patients, which is a lot within 10 days. But the problem here comes with after, say, 30 days, and I get 10 to the 14 infections, which is more than the whole population of the world. Is that good? Of course not. That's a problem, right? So what's the problem here? So the problem here is that I don't have an upper limit of how many people can get infected, right? So there's a limit that how many people can get infected, and the upper limit is the total population of the world. So we need to introduce something like that. So let's take a look at a new model, which is a step further than the exponential model, is that it's called SI model. So now we have two populations. One is called the total population or susceptible population, which is denoted as at SN, right? So starting from day 0, SN equals to N0. That's the total population that can get infected, or it's called susceptible. And at day 0, and there was initially I0 infections in this case, right? And now I have I0 infections, and now because my patients can have contact with people without social distancing. They just freely talk to people, go to restaurants, and you can get new people infected. So the new infection through the contact rate is actually lambda times I times S. Right, so I times S because it's a proportional. So new infection is proportional to both the infected and the susceptible in this way. So every day, these are new infected people created, and then these are removed from susceptible and added to I. So these are the new infections added to this, and they're removed from susceptible in this way, right? So that's a one relation here, and lambda here is called contact rate. So the higher lambda is, means that the more contact between the infected people and susceptible people, and then you create more patients every day, right? So let's take a look at this table. At day n, the susceptible is SN, infected is actually IN in this way. So based on the definition using the contact rate, so the newly infected at that day will be lambda times I times S in this way, right? So now based on this relation, what's the change of IN in this way? Which is very straightforward. You just add IN with the newly infected. So IN equals to lambda times I times S in this way. All right, so the susceptible is also easy to calculate because these new people becomes infected and they're removed from susceptible. And then this is the equation for the susceptible in this way, right? So based on this relation, and you can see that we can get a set of recursive relations for both SN and IN in this way. So this will be SN plus 1, which is a new day, the next day equals to SN minus lambda times IS, and I is the other way around. So you can see that, let's just take a look at the infected. So the number of infected on day n plus 1 equals to day n plus the newly infected, which is lambda times I times S, right? Because this is added to N and the total population must be conserved, right? So these newly infected people are removed from Sn. So that's why you see a negative sign here in this way, right? So this is the recursive relation for the SI model, which has only one parameter called contact rate. So every day, this portion of newly infected people are created from the susceptible population and moved to the infected population, right? So in Python, to do that implementation using the Python model, which is also very straightforward, it's just a quick one-step extension from the exponential model. Right, so this is the basic code we are going to use, and let's go through this. So first, these parts are called initialization. So I give a total population, 10 to the 7, that's 1 million people, and 70, that's T, that's a simulation day. And I create two NumPy arrays, the same size as the total dates here. And that's called the susceptible ratio, or the susceptible infective ratio. And that's infected. And lambda is the contact rate. Let's use 0.5. And I'll show you, what kind of lambdas to use based on other studies of epidemics. So let's first calculate initially infected people. So because I is a rate here, so I0, let's say there are 5 people initially, and divide by n, that's the infectious ratio at day 0. And susceptible ratio will be 1 because that's n by n, it's 100%, right? So the next part, this is the main engine that solves that recursive relation for the equation. So you can see that Sn plus 1 equals to Sn minus lambda times I times S. If you still remember that these are the newly created infected people, so they're removed from susceptible population, and they're added to the infected population, right? So here, that's the infected on day n, and that's the newly infected added at day n. That's removed from the S and added to n. And these are the plotting codes, right? So based on this, the mathematical form of the SI model is slightly more complicated than the exponential model, and you have S, which is susceptible as a function of time, and I is infected as a function of time. So the time rate of change in ST equals to the contact rate times the S and times I. It's because the newly created patients or infections are proportional to both the susceptible population and the infected population. Right, because you can see that if there's initially no infection, and this will be exactly 0. And also I is the same thing, but they have different opposite signs. And then if you use the recursive relation based on the definition of I dot here, so I dot is basically IN plus 1 minus IN equals to lambda times S and I. And you move this term to the right-hand side of the equation, and you get exactly the same recursive relation as we did in the Python code. Right. So after running this code, and let's say if we start from 0 with 5 infections in this way, and you can see that this is actually the time variation of the infected ones and the susceptible population. So when I plot this, I multiply n back to I and S. Right? So I back from a percentage to the population, actual population. So you can see that after about 50 days, and everyone's infected and the susceptible population goes down to 0. So there's no infection anymore. And basically the lambda here, which is the contact rate, determines how fast the infection is. And you can see that from -4 to -5, 0.4, 0.5, 0.7, and all the way to 1.0. And you can see that when the lambda, which is the contact rate, is about 1.0, and it takes about 10 days to get 1 million people infected very effectively if you don't do any measure in this way, right? So this is basically the SI model. So you can see that lambda determines the rate of infection, and people get infected, and the numbers don't go all the way crazily exponentially in this way. So What is the problem here? Right, the problem here is that in this model, everyone gets infected and they keep getting infected, so nobody gets cured, right? So now we need to introduce one thing. Another term is some people gets cured every day, right? So the first one is that if people gets cured and they don't get immune, so that's called the SIS model, right? So the assumption here, starting at day S, on day N, there's susceptible population is SN. So because of contact, right? So lambda times, oops, this should be lambda times I times S. That's the newly infected population. And that population gets added to the total infection rate. Right? So on that same day, because we have medical treatment, right? So people gets cured. Now we have introduced another parameter called gamma. So gamma is called the cure rate. So every day, gamma times I, that's the number of people gets cured, right? So this is the new infection. This is the cured. So they should be removed from the I, or this should be removed from S. So the problem is that the assumption is that those people get cured, they don't have immunity, right? So when people don't have immunity, they can be infected again. So they come back, they went back to susceptible in this way. So once they get killed, and this population goes back to S, right? So now let's take a look at this table. At day N, we have SN and IN. So that's susceptible and infected. So the newly infected is lambda times I times S in this way due to contact. And cured one are gamma times I, because that's a portion of the patients gets cured in this way, right? So now we know that for the S at day n+1, starting from Sn, and first you get lambda times I times S gets infected, so these are removed from S, but because of the cured are still susceptible because they don't have immunity, so these are the cured added back to S in this way. And you can see that for I, that's the opposite, right? So that's the increase in the number of infection, and that's the decrease in the number of infection due to cure. Right? So if we write this relationship or description to a recursive mathematical equation, and that's what the SIS model look like. So Sn+1 equals Sn minus lambda times I times S plus gamma times I. And I, the next day, is the opposite in this way, because the people, you move one population to the other and the other way around. Right? So the infected people in this way will be next day will be based on the infected number on day N, and that's the newly infected day number between day N+1 and day N, and these are the cured on day N in this way. And you can pay attention to the sign differences in different populations based on this plot. Right? So because the assumption here is that the cured person, they don't have immunity. So when they get cured, they got removed from infected ones and they get added back to the susceptible population this way, right? So let's take a look at Python implementation of the SIS model. Is that it's the same thing, you get initialization, you got S and I, and lambda is the contact rate, let's say 1.0, and gamma is 0.3, so which means that every day, 30% of the patients are cured in this way, right? So you can see that, let's say, initially got 45 infected cases, and susceptible is 100%, everyone's susceptible. So you can see that this is the for loop does the recursive calculation to evolve the S and T to the next day. And you can see that for I, starting from I equals to N, and plus lambda times I times S, and minus the recovered one, which is gamma times N. So you can see that from the view of this for loop set, T is going to step through this range. So at first one, T is going to be 0. So which means that I1 equals to I0 plus I0 times lambda times S0 minus gamma times I0. And then we get I1, right, and S1. And then now T moved to 2. and you got I3 and S3, and then just keep going and going all the way to t to the minus t minus 2, and you get st minus 1 and it minus 1, right? And then you do the plotting codes here, which is relatively straightforward. And remember that these are the ratios, so I time multiplied by the number of population to get actual population. Right? So the mathematical form of the SIS model is also similar to the SI model, except I have two additional terms based on the cured ratio. One is removed from the infected species and added back to susceptible. And these are the time rate of changing ST, and that's called the time rate of changing IT. And if you use the relation based on definition of the change in time rate of change, which is in plus 1 minus n at day n, and you get this recursive relation exactly as we talked about previously. All right, so the Python implementation of the SIS model is also very straightforward. And we look at this. These are initialization. And then when you got this code and you run it, and we're starting from 45 people infected, and then you can see that after 70 days, and you can kind of see that the infected ratio goes all the way from 0 to about 0.7 million, and then it's saturated. And then the susceptible ones drops from 1 million to about 0.3 million and saturated in this way. So you can see that with these parameters, it takes about 20 days to get a population that's constantly infected at about 70%. So what happens here is that as S drops, and to some extent, every day you get same amount of people get infected and same amount of people get cured. So you have kind of a dynamic balance between I and S, so they tend to become constant in this way, right? So that's how the SIS model works. And you can see that the final number of people gets infected is determined by the lambda, which is the contact rate, and also the gamma. Well, the gamma here. Also, gamma here is basically recovery rate. It's a depending on the level of the medical treatment, right? So the higher the gamma is, the more people gets cured after the infection, right? So you can see that higher gamma is, and you get a lower percentage of infection because people gets cured very quickly than newly infections in this way, right? So what's the problem here? It seems to work, right? If you have a lower contact rate and you have much smoother changes in the infection, you have a higher recovery rate, you have a much lower final infected population. But what's the problem here? Well, the problem here is that this is mostly not unlike if it's a flu or even the COVID-19, is that when people get cured, they get some kind of immunity, right? So the SIS model ignores the immunity here, which does not work for most of the epidemics, right? So we need to go to the immunity model, which is called SIR model. Right. So the SIR model, we have three populations. One is susceptible, called SN. The second one is infected, called IN. And then the last one is called removed, or you can see it's recovered in this way, called RN. So the assumption here is that the total population is fixed, it's N0. So at day N, because we have SN, IN, and based on the contact rate lambda, and lambda times I times S, that's the newly infected people created through contact, right? So these are added to I. And because we have medical treatment, so gamma times IN, that's the number of people gets cured. And those are removed from I. And because we say, now these people are immune and they no longer can get infected. So they're no longer a population of susceptible. So they don't go back to susceptible and they go to a new population called removed or recovered. So they go to this population, right? So based on this picture, and we can say this is a table to fill. So at day n, I have three populations, three groups: SN, susceptible; IN, infected; and RN, removed from the picture. And then you can see that through contact, the newly infected is lambda times I times S. And the cured is gamma times I. And they're immune, so they don't go back to S again. Right? So now let's make the recursive relations. At day n plus 1, Sn plus 1, which is susceptible population based on this relation, you remove this portion from S. So that's Sn, and remove that one. Remove this one, lambda times I times Sn. So In would be slightly more complicated. So you get new infections, which is lambda times I times S, that term. And then you have also people removed from I, which due to cure. So that's gamma times IN in this way. So add this term and remove that term. And Rn is relatively easy. And you just have new people added to Rn, which is Rn plus gamma times In. Right, so that's the newly removed ones, and they don't go anywhere else. They don't go back to S in this way, right? So the recursive relations here goes like this, and you can see that. Let's take a look at the infected ones. Is that between day n plus 1 and day n, these are newly infected through contact, and basically it's that term. And then you also remove gamma times In due to medical treatment, so these got cured and recovered or whatever, removed from that. And then you actually remove this from S and from gamma as well. So the mathematical form for the SIR model have three functions, S, I, and R. All of them are a function of time. And the time rate of change of S is a function of the contact rate, tongue contact rate, and SNI. So lambda is the contact here. And for I, it's not just to create, it's creating new patient through contact and also remove patient through recover. And also the removed one, every day you get new recovery due to the treatment, which is gamma times IT in this way. All right, so the implementation of the SIR model are also similar to the one at SIS or SI model here. It's just you need to include a new array, which is called R, right? So that's the N, which is the total population. So 10 and 5, that's basically the newly infected, and these are newly infected. That's the total population. And I'm simulating 170 days. It's like 5-6 months. And now I am creating three variables, create three arrays with all zeros, in this case, S, I, and R. And now I'm using contact rates of 0.2586 and recovery rate 0.0821 in this way, right? I'll tell you where these numbers are from. So initially infected people will be 10, so the ratio will be 10 divided by n. And initially infected population will be its all, which is S0, which is basically 1 in this case. And now this is the for loop does the iterative solving of those equations, and you can see that I'm moving from day t to t plus 1 based on these equations, right? Just pay attention that it's based on the values at day n, and the newly infected at day n, and the newly recovered at day n in this way. And then these are the plotting code. I'm multiplying S, I, and R by the total population n, so I go back to the unit, which is total population in this way. So if you look at this, and then these numbers are actually from SARS data. So these are actually from curve fitting and statistic studies based on SARS. And then you can use these studies for coronavirus at the moment. And you can see that when we introduce the removed population, and you can see that when the infected population has a peak after about 3 months, and then after about 3 months, you see the peak and it actually drops in this way. And eventually it takes about 5 months to have the epidemic pass through, right? So this is basically the, if you change the lambda, if you increase the lambda, and you will make the peak occur earlier and higher, and you increase gamma, and you make the peak lower and flatter. Right, so that's how also the ways that people think about how you deal with epidemics in this way. So here the lambda determines the rate of infection, and gamma is the rate of cure. And in this picture, and those will affect the shape of those curves, and also affect how people think about dealing with epidemics and make policies in these ways. Right. So it sounds like a pretty nice model, but what's still missing here? Something's still missing. Think about this. Right. So in the real disease, and we have talked about immunity, infected and people get immune when they get cured and they get immune. And there's one thing missing here, or there's more, but one apparent thing missing here is that all the diseases like COVID-19, it has an incubation period, right? So when people get exposed and they don't have symptom yet, so you don't know, they're not infected yet, they just got exposed. It takes days to get infected in this way. Right? So we need another population, and that's called SEIR model. Right, now we have more parameters play. So the assumption here, now we have 4 populations. One is called S, susceptible, and the second one is called exposed. So exposed are people who had the virus but don't have symptoms yet. So they're called in the incubation period. And the third one is infected, which means they're sick. Right? And the last one is removed because they're immune. Right? So now the assumptions here, every day we have newly exposed population. People get exposed to the virus. They got the virus due to contact, which is lambda times I times S. And these got added to the exposed population, right? And in the exposed population, there are a couple of people, some portion of the people will start to show symptom and they become ill. So that's called sigma times exposed number. So that's the percentage of exposed people gets the symptom, right, in this way. So sigma, you can usually regard as 1 over the incubation period. For example, for SARS, it was 1 over 4 days of incubation. And for the COVID-19, it'll be 1 over 14 in this way. Right? So the newly infected becomes a population of infected ones from the exposed population. Right? So you can see that the infected population, and as we did before, and gamma times I gets cured. So these are actually removed from the story in this way, right? So now you can see that in the suspected ones, you remove this population. And for exposed ones, you're adding this population by remove this population. And for the infected ones, you're adding this sigma A, but you remove gamma times I. And for removed ones, you just add that one, right? So let's make a table here. You can see that I have 4 populations right now. It's getting more and more complicated, but the basic idea is the same. And you have SN, EN, which is exposed, IN is infected, and RN is removed. And now I have 3 delta population created in S, E, and I. So newly exposed will be lambda times I times S. And the newly infected will be sigma times E, because infected are generated through exposed people and they have incubation period. Right? So sigma is usually 1 over the incubation period. For the coronavirus, you can see it's 1 over 14 or 1 over 10. Right? So the cured is the same, gamma times I. So I have 3 parameters, lambda, sigma, and gamma. Once you contact, incubation, and cure rate. Right? So at day n, Sn, and we can write down the equation about Sn equals to Sn plus 1 equals to Sn by remove 1 population. And then EIR, you can also do the same thing by putting these populations to the right version of the population. And then you can get to the recursive relations and write down a code to solve that equation. So I'll leave this as a practice one and also part of the homework.